Hello class, this is Hiber Fonseca, your TA for Chem 2124. Today I will be talking about crystallization. What is a crystal and what is crystallization? A crystal or crystalline solid is a solid material where molecules are arranged in a highly ordered structure, forming a crystal lattice. For this class, you don't really need to know all the kinds of crystal lattices and all their nuances that you can learn about in, for example, in organic chemistry. But you do need to know the process of crystallization, which is the process of crystal formation. And crystals push each other, I guess. You could describe it as that, and how these chains that you can see here, they first this crystal forms and then it pushes the other ones to start forming as well, to come out of 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 their solvation sphere. In like if this was, if for example this was the compound in a liquid solution, then once one crystal forms, then it can push the other ones to become more crystalline. They might also be amorphous, but um, a lot of a lot of compounds become like this. For example, ice. I'll go back to ice a lot because it forms an ordered structure through through freezing, right? It's a similar occasion that happens with a lot of the compounds that we'll see. Table sugar is sucrose. You may have noticed the difference between powdered sugar and crystalline sugar. Crystalline sugar is produced via crystallization of the sucrose solution. So if you put sugar in water, the powder, I'm pretty sure you can actually convert it to sugar crystals by the method described here. To really understand crystallization, you need to know about solubility, and so you need to know about polarity and how temperature affects solubility. To do crystallization, the first important consideration is selecting the right solvent to dissolve the compound and make a homogeneous solution. Not every organic compound will be soluble in every solvent. Which compound will be soluble depends on polarity. Polarity is a separation of electric charges, leading to a molecule having an electric dipole moment. Some molecules, like water, for example, they have permanent dipole. They have permanent dipoles. Um, so, like for example, excuse my drawings. Um, these arrows that I just drew around the water molecule, they represent dipoles. So the electrons around the hydrogens, they are bound, they're closer to the oxygen atom because oxygen is a very electronegative atom. So what it means is that it's pulling the electrons inside these bonds. Oxygen is pulling them closer to itself. So then there's a that side of the molecule is more negative, and the side where the hydrogens are is more positive. So then let me erase this. So then the molecule has a dipole, a permanent dipole. The electric dipole moment is a measure of the separation of positive and negative electric charges. Like I said, the more polar a molecule is, then that pulling from one side to the other is stronger. So then in water is a very polar molecule because oxygen pulls the electrons closer to itself much more strongly than the hydrogens can pull the electrons towards itself. The more the higher the dipole moment of a compound, the more polar the compound is, again. And how does that relate to solubility? Well, I'm sure you have heard about like dissolves like. Like dissolves like is very important in organic chemistry. In other words, the more polar a compound is, the more soluble in polar solvent it is. And the more nonpolar the compound is, the more soluble it is in nonpolar solvent. Like dissolves like. Polar dissolves polar. and nonpolar dissolves nonpolar. A polar solvent will dissolve a polar compound, and a nonpolar solvent will dissolve a nonpolar compound. Water will dissolve compounds that are very polar, whereas hexanes will dissolve polar compounds that are not as polar or are not polar at all. But temperature is very important in this solubility. All compounds have a solubility constant, which is affected by temperature. You might remember the solubility constant and equilibrium constants from Gen Chem 1, maybe no, actually Gen Chem 2, right? Um, yes. Here are some examples of solvents. Water, as you can see, is very polar, and you can explain it like the way I said. No, you have two dipoles here going towards oxygen, and the geometry of the molecule allows them not to cancel. That's a consideration, yeah, that you will see in your lecture that well, you can consider right now. But also the boiling point of water is something else that you must consider when you perform crystallization. For water is 100 degrees Celsius. For dichloromethane is 41 degrees Celsius, and for hexane is 70 degrees. Now you should know these boiling points, especially if you're working in a research lab, because you're going to be performing a lot of crystallizations, some extractions, and you need to keep in mind all of these values at all times, especially if you will have to improvise or if you are trying to come up with a new process. So dichloromethane is very popular in the labs. You could say it's probably my favorite solvent, or maybe second to acetone. But it's very important because it's moderately polar, and it will dissolve a lot of the compounds that I am working with in the lab. Um, water is just messy, but it will dissolve highly polar substances. So you can actually wash things with water, but you can also wash things with dichloromethane, especially things that you don't want anymore in whatever you're working with. Acetone, for example, is another compound that is moderately polar sometimes, uh, and it can wash things very effectively. Crystallization is definitely a purification technique, and it is performed to purify a solid compound. This is an important distinction, um, and it's only applicable to a compound that is solid at room temperature. If it's liquid or gas at a room temperature, then it cannot be applied. You cannot crystallize uh, the way we're going to be doing it, and you'll definitely see why, hopefully. Um, but a solvent, we have to select a solvent depending on the polarity of that solid compound. For example, water, a highly polar solvent, is a good solvent for a very polar compound like benzoic acid. However, you have to factor in temperature. A solvent needs to be selected in such a way that the solid should be soluble in a hot solvent and much less soluble in the cold solvent. This is another reason why you have to memorize the boiling points of many of your solvents. Impurities should be soluble even in the cold solvent. So again, when you have your impure compound, you'll put it in a solvent, you'll dissolve it, right? And you're going to warm it up so that both the impurity and the compound dissolve. Once they are dissolved, eventually you will cool them after doing some stuff to them that you'll see. Actually, you can see it right here in the drawing. Um, and so the solvent will still hold on to the impurity, but your compound, the compound that you want, you can separate it here on this filter paper that says here. And so you have the solid crystals here, the pure solid crystals, and the impurities remain in the solution. This is very important, and hopefully you can see why selecting the solvent is very important. It all depends on the solvent and the nature of the impurity in your compound. If the solvent, if the impurity is more soluble in the solvent, then you got your day set, because once it gets hot, once you heat it up, the impurity will most definitely dissolve in the liquid, and your desired solid will not dissolve that well in the liquid, which is desirable, because then you, once it gets cold and the more crystals form, you'll put it here in the filter paper, and these very pure crystals will remain, while the impurity will still remain attached to the solution, right? Um, that's of course if the impurity is much more soluble. There's some cases where the impurity is just as soluble as your desired compound, and that's where it gets really complicated. But luckily, in this experiment, we have benzoic acid, and its impurity is easy to separate. Thus, solid plus impurities will be dissolved in a hot solvent to make a solution. And when the solution cools down, only the solid will be crystallized, but impurities will remain soluble in the solution. Again, this depends on the nature of the solubility of the impurity. But I mean, if you are even going to attempt a crystallization, you should know a thing or two about your impurity. So then this is why we're doing this, because we know that impurity is sort of more soluble in the solvent. A simple filtration will separate the solid crystals from the impurities, which is now the impurities are now soluble in solution. When you perform an experiment, you have to make sure that you're always thinking about why you're doing this, and if this is the best way of doing this. So as I read these instructions, please take notice of why you might be doing these things, and I'll comment a few things, but you must be thinking already, especially hopefully you read, but if you haven't, start thinking about why you're doing these things, right? So you're gonna have two beakers. In a 50 ml beaker that is not bigger than 100 ml, take around 0.5 grams of impure benzoic acid. You should always write what quantity you're working with. So in your laboratory notebook, you would have written this, and then you add 20 ml of water, and you heat on a hot plate to dissolve the solid and make a solution. You may have to occasionally add water in 2 or 5 milliliter portions to maintain the volume at around 20 ml. Do not let the solution dry out, and do not let the solution get concentrated below 10 ml. Also, you don't want to add a lot more solvent, in this case water, because then it's much harder to form crystals if you add a lot more solvent. Um, Therefore, you have to control your heating, but you also have to make sure that you only add uh, 20 ml of water, right? In the second beaker, you you add around 25 ml of water, and you keep it hot. Uh, you should keep it boiling. This hot water will be used before and after the gravity filtration that you'll be doing shortly. Um, in the flask where you'll conduct the filtration, you set it up this way. You set up a funnel up here, and you stabilize it by a clamp. Um, Before the actual filtration, you soak the filter paper that you put in here. It's like a cone-shaped filter paper. Well, it's actually round. It's a circle, but you make it fit, so you shape it like a cone. You soak the filter paper thoroughly with hot water, and then quickly do the filtration of the benzoic acid solution. So from beaker 1, you should not see crystals here. You should not see crystals here. The purpose of this is to get rid of solid impurities that might already be here in this solution. Impurities that might not be soluble in water, right? So you're not just dealing with, again, you have to be aware of the nature of your impurities. Um, but I guess in case if you don't know, but you know that there's some insoluble stuff there, you have to make you have to first do this gravity filtration. It's sort of as if you're making coffee and you're putting coffee here, and you don't want to eat those all the solid stuff that comes with coffee. You just want to drink the coffee elute, right? Of course, you don't want to drink in the lab, but it's pretty much the same concept, right? If you observe any premature crystallization on the filter paper, that means that there's benzoic acid accumulating here, and so you will lose some product, and you don't want that, right? So you have to use some more hot water from beaker two because again, benzoic acid is soluble in hot water, right? So then that's why you keep this second beaker. After gravity filtration is performed, the Erlenmeyer flask contains your benzoic acid solution, from which pure benzoic acid crystals will be formed. But to ensure a complete crystallization, the solution concentration must be optimal. It cannot be too high. Crystallization never occurs from a too dilute solution, so you must make sure that your solution inside of the flask is no more than 25 ml. Use the marked line of your flask to gauge the solution volume. If the solution is too dilute, i.e. the solution volume is more than 25 ml, then you must keep heating the flask on the hot plate until the solution volume comes down to near 25 ml, meaning that the solvent will evaporate. This step is important. Once you reach the desired volume, take the flask away from the hot plate and let it cool slowly on the bench top. Also, the cooling is important. In most cases, if you follow the above mentioned procedure, then you should observe the crystallization when the solution cools down to room temperature. If you do not observe crystallization, then you should cool the Erlenmeyer flask further in a bowl of ice water. You may gently scratch the inner surface of your flask with a metal spatula to initiate crystallization. Also, something you can do is if you have some reference benzoic acid, if you have some benzoic acid just lying around, you can use it in a process called seeding, so that you put a little bit of the crystal, a very minute amount, so that you don't mess up your measurements, and it will probably initiate crystallization. It will push the other benzoic acid molecules to precipitate out and come out of solution. But crystallization indeed can sometimes be a slow process. So now you're ready to collect the crystals by vacuum filtration. You will need a Buchner funnel, you'll need your filter flask, and you'll need these special rubber stoppers, adapter cones, that you put between the flask and the Buchner funnel. You always need to clamp your instruments, and you'll need a hose that goes to the vacuum. You set it up as is in a 150 milliliter filter flask because it must have this glass protrusion here, so that the hose can be attached to it. You need to use a thick tube. Some of these tubes cannot bear a strong vacuum, so you make sure that it's a tube designed for that. You must stabilize your system with a clamp, because the Buchner funnel is heavy, and especially if it's a bigger one, there's different sizes, and so it might tip to the side, right? You'll also use the right size rubber adapter. This one, there's different sizes, and therefore the size of the filter paper must also be proper. Sometimes especially if your laboratory is not equipped with the specific size. You might have to cut them with some scissors. And just before filtration, you have to soak the filter paper to ensure that liquid doesn't some of the liquid doesn't get stuck up here, and so you make the process faster. While vacuum is on, you dump the crystals with the mother liquor, the solvent, and use some extra water. You can put some more water in here to make sure that all the crystals have come out. And then you just leave it here drying for 5 minutes. So the crystal is gonna be here, and with the vacuum on, creating more pressure, the crystals are going to essentially be drying here, right? Sometimes something else that you want to do, especially when working with other impurities, more complex impurities, or with sometimes you couple the solvents. So you use, for example, water and ethanol, or ether and ethyl acetate, for example. You might want to wash the crystals, so you put some of the solvent to get rid of the other solvent, or you'll just do more rounds of washing before drying. But since this is simpler, you just dry, you just let it sit, you just let the crystal sit on top of that Buchner funnel with the vacuum on. So after you thoroughly dry them, you must take the weight of those crystals. So you turn off the vacuum and you carefully remove the filter paper, and you probably want to transfer the crystals on the filter paper to a watch glass, probably a pre-weighted watch glass, or a watch glass that you then weight, and then you put the crystals on. A lot of these compounds, if you do this in the hood, they might be in the fume hood. They might be blown away by the air, by the inward air flow of the hood, and your crystals just disappear and your hard work is gone, right? So you always need to be careful of these gusts of air. Sometimes even when you're moving them and your lab mate just walks by, creating some air, and your hard work for the day is gone. Right, so it's pretty sad, but you always have to be careful. Usually, when you're using some weighting paper, you wrap it in such a way so that you protect your crystals, right? So anyway, then you take it to to the balance room and you weight the crystals, and you, of course, you keep good records of it in your lab notebook, and you just use this formula. It's just a percent. You just calculate the percent recovery, the initial weight of the impure benzoic acid, um, divided into the final pure weight of the crystals. And that's pretty much it. Uh, and and finally, we have waste and chemicals disposal. Solid waste, as you might imagine, is the benzoic acid itself, the crystals, and the filter paper that you use to filter it. And then there was no glass that you might have broken, unless you broke the watch glass, for example. Aqueous waste is all of the water and the impure benzoic acid in the water, and then you would make sure that the balance area is clean. And that'll be all. Hopefully you learned something new today. Thank you very much for listening.